Okay, we were discussing this amortized analysis. Okay, amortized analysis we took in the last class, and we have seen this aggregate analysis there. Aggregate analysis. One example we have seen aggregate analysis, one concrete example, and we have discussed that okay, there are several methods with which we can proceed for this amortized analysis. One is this aggregate analysis and another is this potential method. Okay, so that potential method we will discuss today. So this potential method we will discuss right now. Okay, so this the potential method works as follows. Potential method. So as usual, this amortized analysis, the very best reference is the book CLRS, okay, for amortized analysis. So we have seen that in this amortized analysis, what we think that okay, we are performing a sequence of n operations, okay, and then that sequence of n operations we are performing starting with an initial data structure D0. Okay. So in our example, this as we will be discussing this amortized analysis with the help of again that stack operations, push pop and multi pop operations. So okay, so push pop and multi pop operation, and here this example of D0 is our, in our example, empty stack is our D0. That means whenever we are starting the sequence of n operations, initially the data structure is that data structure that we are discussing, that will be empty stack. Okay, and after first operation the stack will be in D1 state, or will be having D1 data structure and so on. In the second operation the stack configuration will be changing. So we are calling that thing is the D1, and the next operation it will be D2 and so on. Okay, we'll see this is initially we have to build up some kind of theory, and then again we will be coming back to this example that how we are analyzing with these stack operations the amortized cost. Okay, now another thing is that we have assumed that we are going with a data structure, right? We are going with data structure, and initial data structure is D0, and here also we need a function, potential function phi, okay, that maps each data structure di to a real number phi of di, right? So so for example, in our example we can define the potential function phi on a stack to be the number of objects or elements in the stack, right? So in our case, if the initial data structure, if we are applying this phi function in this empty data structure D0, then the phi of D0 will be definitely 0, okay, because phi function is counting the number of elements in the stack, right? So that is the way we are defining a phi function here, right? So we are so now little bit this data structure and this potential function is little bit clear to you. Whenever we will be taking the concrete example again, then it will be much more clearer, okay, what is happening. But to have a potential method going on, you have to have this data structure ready, and also you have to have this phi function ready, right? And that is the main important factor whenever we will be analyzing amortized cost with potential method. If we can figure out phi, what is phi function and what is the data structure we will be maintaining, then our job is 80% done. Other thing will be a routine formulation, right? So here this whenever we are dealing with stack, as the stack after each push pop and multi-pop operation, the stack is changing, okay? So that means the data structure we are applying, we are having one data structure which will be maybe corresponding the state of this stack, right? And what is the behavior of that state we are looking for, that will be representing this phi function, okay? So that means the sole idea here is this how many number of elements are there at that point in the stack, right? So you see, whenever I am pushing one elements in the stack is the data structure is changing and it is accumulating something, right? It is summing up something, it is adding something to the data structure. Whenever I am popping, it is decrementing the data structure, that means in terms of the number of elements, right? So that's why this is becoming this data structure and phi function here. And based on that we will be designing our amortized analysis, okay? If we can define that, then it would be easier for us to analyze for a sequence of n operation what is happening. So that's why we are defining this in that way. This is one way of defining. Say if somebody is coming up with other phi function and other data structure for the same problem and can show the behavior of this amortized analysis, that is also fine, okay? Anyway, so here we will perform in operations as stated earlier. For each I equals to this 1 to n, we let Ci be the actual cost of the ith operation and Di be the data structure that results after applying ith operation to Di minus 1. So whenever we are, say, at any point, any ith iteration, okay? So this is so far whatever is done, and now we are doing the ith iteration, okay? So in this ith iteration, if it is multi-pop, if it is pop, if it is push, then if it is push operation, okay, if it is a push operation at that time, so in that case what we will be doing, we will be pushing one element on top of this, right? So that will be involving one actual cost. So this is I am pushing the element. And then this, as we have seen, that this is Di minus 1 data structure, and whenever I will be pushing this, I will be having the state like this, and this will be our Di. Okay. So Di be the data structure that results after applying the ith operation to Di minus 1, right? Okay. So with this, what we are doing is we are trying to establish one mathematical formulation of this potential method, and by far this potential method is the most robust method of analyzing this amortized cost, okay? And people are also applying this potential method in other analysis of algorithms as well. Okay. So potential method is a very important abstraction of analyzing amortized analysis. And many new papers are applying whenever they are analyzing this amortized analysis, they are employing this potential method only. So that's why this potential method you have to know. Okay. So as stated earlier, a potential function phi maps each data structure di to a real number phi of di. Okay. So as we have seen, phi of di d0, that is equal to 0. So it is mapping it is counting the number of elements there in this stack. Okay. So which is potential, so this phi of di, which is the potential associated with the data structure di. So how much potential that data structure is having? Say you are climbing the hilltop. Okay. So you are gaining some kind of energy there. So that potential energy. So that is the idea of whenever we will be accumulating the energy and then we will be releasing the energy. Okay. So this idea, this physical phenomena is coming into picture whenever we are having this amortized analysis being analyzed with this potential method. So the amortized cost, which we are denoting by CI cap, right? CI cap, amortized cost of ith operation. Amortized cost of ith operation with respect to the potential function phi is defined by this. Okay. So CI cap, that is equal to, whenever I am in ith operation, that I am performing one actual cost that I have seen already, that we have seen already. Okay. And then after applying that ith operation, what is the change in potential? So that is phi of di, what is now the potential, and what was previously, di minus 1. So that will be the amortized cost that will be associated with the ith operation, its actual cost and the change in potential. Okay. The amortized cost of each operation is therefore its actual cost plus the change in potential due to the operation, that we have written here. Okay. So that we have written here. Now by equation 1, so this equation 1, the total amortized cost of the n operation. So this is per operation amortized cost. So we are performing sequence of n operations. So what will be the total cost, total amortized cost? So that will be CI cap, and that will be summed up over I equals to 1 to n, those many number of operations. So this is equal to this summation. So this side summation, I equals to 1 to n CI plus phi of di minus phi of di minus 1. Okay. So now we can separate this summation here. So here it is written. So this is I equals to 1 to n, and then this CI is separated here, and plus I equals to 1 to n, this phi of di minus this phi of di minus 1. Okay. So now you see this is remaining intact. I equals to 1 to n Ci. Okay. So I am keeping it inside this bracket because that is within the summation. And now you see this is, if I expand this, expand this one, this whole one. So that means if I equals to 1, it will be phi of d1 minus phi of d0. So this is I equals to 1 plus I equals to 2. It will be phi of d2 minus phi of d1. Okay, and this is the way it will be going on. And whenever we are having phi of n, whenever we are having n, I equals to n, at that time it will be phi of dn minus phi of what will be there? Can you tell me? Phi of dn minus phi of what will be that? Who will be telling?
dn minus 1.
Who, who, who is speaking right now?
Sir, Sohit Kumar Singh.
Sujit. Shuhit.
Sohit.
Suhit. Okay. Thank you for responding. Okay. So it will be dn
Thanks.
minus 1. Right. So dn minus 1. This is. Now you observe that what is happening out here is this. This is getting cancelled out with this. Okay. So likewise this d2 will be cancelled out somewhere down here. Okay. And likewise all the terms will be, so this phi of dn minus 1, phi of dn minus somewhere here, this phi of dn minus 1 will be cancelled out somewhere down phi and dn minus 1. So every term is getting cancelled out except this phi of dn and then this phi of d0 with this minus sign preceded. So that's why it is written that this sum, this phi of di terms telescope. So this is a telescoping series. Okay, this is a telescoping series, and this telescoping series having many different applications in computer science analysis. Okay, so we are getting that okay, this that we have seen that I equals to say 0 to infinity, that xi, okay, when x mod x less than 1. So that is having a very good applications in computer science analysis. Another thing is this method of contradiction and then method of induction, and then this telescoping series is again coming up. So telescoping series, this is very important in many different scenario. This thing comes up. Okay, telescoping series, and so you see this this phi of dn minus phi of d0 is there, right? So this now what we can say is that, so what we have got, this total amortized cost, CI cap, total amortized cost. So that is the total actual cost I equals to 1 to n CI plus this phi of dn minus phi of d0. So this is inside the summation only, right? And this is outside the summation. And now what we can say, this phi of di, CCI cap, will be upper bounded by this term. That means phi of this amortized cost, the total amortized cost gives an upper bound of on the actual total cost, right? So that means this amortized cost is always greater or equals to this CI. When this will be happening? That means when this phi of this will be greater or equals to 0. At that time, this amortized cost is actual cost plus some positive quantity. Okay. So amortized cost, say this is the capital C total cost plus some positive quantity K, right? So what we can say is that C is C plus K is this A, right? And then this C equal to this A minus this K, right? So you see this actual cost is upper bound of this amortized cost minus some positive quantity we are subtracting. So this actual cost is always upper bounded by this amortized cost. Okay, either it will be equal to this amortized cost or less with this A minus K term is coming. So this when this phi of dn minus phi of d0 greater equals to 0, that means phi of dn will be greater equals to phi of d0. Okay. If I take this term in this side, then this is coming. So now we can say that the total amortized cost gives an upper bound on the total actual cost. This is CI. So phi of dn greater equals to phi of d0. What we generally do is we do not show that phi of dn, that is the last data structure, is greater equals to phi of d0. Instead, what we generally show is that phi of di greater equals to phi of d0. Okay, for all I. So for all I means that is including this n, right? So that we generally show phi of di greater equals to phi of d0. Okay. So this is for all I. So all I means it is also including this n, right? So that's why phi of dn will be definitely greater equals to phi of d0. So now this we are going back to our example. So stack operations, we are having a sequence of push, pop, multi-pop operation, push, pop, multi-pop operation. Okay. So we define the potential function phi on a stack to be the number of objects in the stack. That already we have discussed. How phi function is defined on our example, stack example. We are defining that phi is counting the number of objects in the stack. So for empty stack d0, phi of d0 will be equals to 0. As the number of objects in the stack is never negative, as why this the stack, the number of objects in the stack is never negative. How can you ensure? Who will be telling? Where we are ensuring that? Can you tell me? The number of objects in the stack is never negative. How can I claim that? Who will be telling? It was there in the previous class. Whenever we have defined the multi-pop operation also. The number of objects in the stack is never negative. Who will be telling? Anybody listening? Who will be telling? Okay. So let me call and note down who is listening and who is not. Okay. Hmm. Aditya Gupta. No, Aditya Gupta not. Shubhadeep Rudra. Shubhadeep Rudra, are you there?
Yes, sir.
Can you tell me why? I am noting your performance. Okay. Whether you are listening or not. With this, I can figure out that who is listening and who is not. Shubhadeep Rudra.
Sir, because the bottom element should at the index of 0, so stack cannot be in minus negative.
Not exactly.
So basically, we were applying the pop
No,
operation
no, no, no. You
only
not.
till the times the stack
Hello,
was not getting
hello.
empty. Yes, sir.
I didn't ask you. Sohit.
Sorry, sir. Yes, sorry, sir.
Hmm. Voruganti. Can you unmute? If you are not, you are being Voruganti. Okay. Hmm. Can you tell me? Hmm? Ankita Mondal. Ankita. Can you tell me? Hmm? How many of you? Very few people are listening. Okay. Hmm. If this situation continues, I have to adopt another technique. Madhul Raj. Hmm? Everybody's network connection is getting lost. Huh? Suddenly. Hmm. Those who are leaving, they will not be getting attendance today. Shankhadeep Ghosh.
Yes, sir.
Tell me. Shankhadeep. Are you listening?
Yes, sir.
What
Yes,
we are
I'm listening.
what we are discussing? What topic we are discussing now? Hmm? What topic? Hmm. Shornov. Shornov Pal.
Yes, sir.
Hmm. Can you tell me why the stack cannot be negative?
So because we are only popping until the stack is not empty. If the stack is empty, we are stopping it there.
Hmm. Very good. Okay. So as he is telling that okay, and very few people are listening, so that's quite hurting. Okay, you are not listening, and the content is not so bad. Okay, content is not so bad, and whenever people will be asking, there's a Google this. I am I am teaching, keeping in mind that you will be sitting for Google, Microsoft, Facebook, Amazon, and many other companies. Okay, so they might not ask this amortized analysis, but they might be asking you some complexity, and at that time, if you can give some kind of insight on amortized analysis, then they will be very much pleased, and immediately they will be taking you to their research group. Okay, so many people are getting the job. Many people are getting the job in Google, Microsoft, Amazon, but still they are not entering into the research group. So why they are not taking? Because you people are absolutely having good potential, but what you focus on only on coding, mechanically understanding the algorithm and coding. So that's why they are not recruiting you as a recruiting you in the research domain. What they are doing, the research work they are doing, and that is quite fascinating. Okay. So along with this mechanically understanding algorithms and coding, you have to understand also how it is, why this will be working. Okay. Okay, so stack is never negative, as already we have defined that we cannot go beyond the empty stack. Okay, we cannot go beyond the empty stack. That means if the element is 0, we cannot pop any other elements. So that is, by definition, it is coming that the stack is never negative, right? So the stack di that results after the ith operation has non-negative potential. That is phi of di greater or equals to 0, and 0 means that is phi d0 as well. So that what we claimed that, okay, we will be proving that phi of di greater or equals to phi of d0 always for all I, that we have done here. Okay, so that is the stack di results after the ith operation has non-negative potential, right? Because the stack will never be going to the negative state, right? So the total amortized cost of n operations with respect to phi therefore represents an upper bound on the actual cost. Okay, so that is once we have proved that phi of di greater or equals to phi of d0, then we can say that is implying that phi of dn greater or equals to phi of d0. Okay, so this is for all I. This is for all I, right? So that's why this phi of dn greater or equals to phi of d0. And once we have got this, then this CI, this total amortized cost, so this is summed up of this overall I, and summed up of CI overall I plus this phi of dn minus phi of d0. So with this we can say, if this condition is true, then we can say that this total amortized cost of n operations with respect to phi therefore represents an upper bound on the actual cost. Okay. Let us now compute the amortized cost of various stack operations. Amortized cost. If the ith operation on a stack containing s objects is a push operation, then the potential difference will be what? So if this is the stack, this is our di minus 1, and then this one push operation is happening at this time. So what will be the di? So we are having one more element added here. One more element is added here, right, for the push operation. Then what will be the change in potential because of this? So phi of di minus phi of di minus 1. If the phi of di, if the di minus 1, that data structure containing this s objects, s number of elements, then after the push operation, how many elements will be there in this stack? S plus 1. One element I am adding. So what will be phi of di? That will be s plus 1. And what is this phi of di minus 1? We had s number of objects at that time. So this will be s plus 1 minus 1, that is 1. Right? Push operation. So now by equation 1, the amortized cost of this push operation will be, so change in potential for the push operation is this. Amortized cost of push operation will be actual cost. So actual cost is what? I am pushing one element. So that will be 1. And this change in potential will be what? 1. So that will be 2. Right? That will be 2. So this is for push operation. Suppose that ith operation on the stack is multi-pop, right? S comma k. So this is which causes this. So this, whenever I am calling multi-pop operation on s comma k, that means on this stack with k number of objects to be deleted, right? Then what will be the case? The number of elements of the stack or the k. So we have seen that if the stack is containing 2 elements and I am trying to pop 4 elements, okay, so in that case minimum of these 2 will be popped off because stack cannot be negative. So that is what minimum of s comma, k comma small s, okay, small s. So this s is the number of elements in the stack, right, and k is the number of elements to be popped up. So that I am denoting, that I am taking in this variable k prime. So k prime will be equal to minimum of s comma k. So that is minimum of, in our example, this example, minimum of 2 comma 4, that will be 2, right? So which causes this these many k prime number of objects to be popped off whenever I am calling multi-pop operation, to be popped off the stack. So the actual cost of the operation is then definitely k prime, as this k prime number of elements being popped off, right? And the potential difference will be what? So as this is a pop operation, so this di minus 1 will be having more number of objects than di, right? So phi of di will be phi of di minus this phi of di minus 1. That will be, so this phi of di I minus 1 had say s plus k number of objects, or this k prime number of objects, right? So these many elements are there, and whenever I have called this multi-pop operation, so this k prime number of objects have been popped up. So phi of di will be what? This will be having this k prime number of objects popped up. So it is S minus this. So then it will be S minus K prime, right? So this will be minus K prime. So minus K prime. So what will be the amortized cost of the multipop operation? That will be, this is actual cost plus change in potential. So actual cost is K prime number of objects we are popping off. So this is K prime minus the change in potential is minus K prime. So that then it is 0. Okay. So the multipop operation, similarly the cost of pop operation will also be 0. That you count yourself. Okay. So now you see this, what we have done is, so the amortized cost, as we have seen, of each operation is order of 1. So push operation, 2, pop operation, multipop and pop operation is almost coming freely. So it is order of 1. And thus the total amortized cost of a sequence of n operation will definitely be order of n times order of 1. So that will be order of n, right? So here what is intuitively what is happening in multipop operation, why it is 0? Because in the push operation is actually adding one extra credit. That is the top up recharge you do for the mobile phone. Okay. So you are adding one extra credit, and then whenever this multipop operation is happening, this credit, all the accumulated credit being distributed throughout. So that's why it is getting 0, right? And the pop operation is also that is the same way we can argue that pop operation is becoming 0, right? So whenever push operation happening, we are adding credit. Whenever pop and multipop operation, we are releasing the credit. That means we are recharging the mobile phone, and while talking, it is releasing, it is paying off from that, right? And we are not bothering at that time, and we can think of as a thought experiment that each call is happening freely, right? As already we have given the credit, due credit to the mobile phone. Okay. So this is today up to this, and soon I'll be taking one extra class, and we'll continue this week. We'll continue this amortized analysis. Okay.